Hi everyone, I am Yikai Wang. I'm glad to be here to share our work on imaging painting. In this project, we focus on improving imaging painting models in two key ways: reducing unwanted object insertion and preserving color consistency. Let's start with the first point. Imaging painting models can be broadly divided into two groups. The first is reconstruction-based, like MAE, which predicts masked regions using only the unmasked regions. This approach is stable and avoids hallucinations, but often produces blurry results. The second one uses generative models that start from random noise and condition on the unmasked region. This produces realistic and diverse images but may not faithfully match the condition. Our idea is simple. Can we combine both approaches to achieve in painting that is both stable and high fidelity? A simple idea is using MAE in an image-to-image pipeline. MAE first generates an image, which we then add noise and denoise to get the final result. However, the initial latent from MAE is often blurry, and it leads to blurry outputs. But we can find that MAE provides a strong prior for the masked region, so we use MAE's output as a condition to guide stable diffusion more effectively. Our framework first uses MAE to generate an inpainting prior, then we apply a lightweight alignment model to get the diffusion model without relying on text. Another key issue in generative latent inpainting models is color inconsistency. The inpainting regions often show color shifts leading to smear-like artifacts. This occurs in both random and continuous masks, making regions appear too dark or too light. While it's not a big problem in generation, where colors are consistently shifted, it matters in painting, where unmasked regions must match the ground truth. The color shift is caused by the imperfections in the VAE. Here is the original image and its reconstructions. Even after one pass, there is a slight color shift. With repeated reconstructions, the shift becomes increasingly noticeable. In the frequency domain, we can see that the reconstruction already leads to information loss in the low frequency range. We treat decoding as an image harmonization task. The decoder takes a color-shifted image and learns to reconstruct the original. We use the unmasked region to correct the color shift. And does this work? Yes, but it not works in all cases. We found that latent generation is also not perfect, so we should also account for information loss in the unit. And we introduce a latent augmentation. We let the diffusion model generate latents for half of the training examples. To isolate the information loss from generation loss, we condition on the full image and sample from large noise in one step, so the generated latents reflect only information loss, not random content. Now we have a better decoder and we can preserve the color consistency, and this decoder is suitable for general text-based inpainting and editing tasks. Our whole framework is named as ASCA for Aligned Stable Inpainting with Unknown Areas Prior. Here are some generation results. You can find that our results are more stable and realistic, and our method is better in different cases. Here are some comparison results with other methods. We introduce a new benchmark to evaluate inpainting models, along with two metrics to assess unwanted object insertion and color consistency. Please see our paper for details. In summary, ASCA enhances imaging painting with color consistency and mitigate object hallucination, while leveraging the generation capacity of the frozen painting model. For context-stable alignment, ASCA aligned the stable MAE prior with generated models to provide a context-stable estimation of masked regions, replacing the text condition with MAE prior. For color-consistent alignment, ASCA reformulates the decoding from latent to image as a local harmonization task, train an Inpainting specialized decoder to align masked and unmasked regions during decoding and thus mitigate color inconsistencies. That's all. Thanks for listening.